detection for unconstrained, for unconstrained video streams with overlapping cube proposals. This was mainly built by Lee Jun, Kevin, and Wenhe, guided by Alex Hopman. We share the same advisor, and my name is Salvador Medina. They couldn't come here today, but I've been part of DIVA before. There we go. So in this case, the system, what it tries to do is activity detection in unconstrained videos, meaning that they're untrimmed and with large fields of view. And mainly when you are trying to do activity detection, you consider three aspects: the temporal localization, also localizing spatially the activity, and classifying this action. When systems are built, they're built towards two different tasks or main goals, which could be a strict target or a loosened target. In the strict target, you try to detect all the atomic activities and then bipartite make a bipartite match between the predictions and the ground truths. For the loosened target, you detect either an atomic activity, such as standing up, or continuous repetitive activities, such as walking, running, and there's even people reading, right? They're moving their hands when they're reading something. And then you try to match multiple non-overlapping predictions to the ground truth. So the Argus++ framework looks something like this. And the way it works is first you take the video stream, then run an object detector from which you start tracking the objects. Once you have all these tracklets, you can make a proposal generation. And I will talk further into the details, and that's the main core of the Argus++ framework and how we do the proposal generation in there. Then we go through a proposal filtering, taking advantage of foreground segmentation. So we detect what is not background related and filter out those proposals such that we can make activity recognition. But given our proposal generation method, we need to duplicate all of these activities recognized and finally classify such that we can have an activity prediction. So as I mentioned before, we make cube proposals here whenever we're trying to build the proposals. A proposal in our framework is just a candidate region where an activity may occur. And we also consider a proposal to be a processing element for the activity recognition. In our case, our spatiotemporal cube proposal is just a 6-tuple, which is defined by the boundaries given by the top left corner, the bottom right corner, the start of the activity and the end of the activity on time. However, we call them cube because the fixed temporal duration, the temporal duration on these cubes is fixed when sampled all the time. So this doesn't change. And this is a huge difference against tubelets because tubelets can have like a really different duration. And the advantage that you get through this is that you have much simpler, you make the problem much simpler than actually using the tubelets or activity instances. So for the proposal generation, what we did was get a proposal sampling just by getting a dense overlapping sampling over the untrimmed videos. And this ensures the completeness and coverage of any activity distance because you have all these overlapping cubes. But however, as I mentioned before, this will bring up a lot of proposals, which then you can refine. And the way that we do it is just put a track ID in the central frame with respect to each temporal window, which is fixed. And then we enlarge the bounding boxes across the window spatially. And let me show you. So for instance, how do we build this proposal from this example? So you have a car which is about to turn to the right. However, the region that is not grayed out, that's the proposal that our system comes from. And the way that it does it is first you subsample the frames and then, First you subsample the frames. Then you start building the cubes, which are fixed in size and duration. And as you can see, the cube is moving along in a diagonal from left to right, top to bottom. And also it's expanding through time. So you get all of these cubes and you at some point mesh them together during the framework and you get that proposal down there. Once we've got these proposals, what we would like to do is to filter out which are relevant. And one of the ways that we do it is through a foreground segmentation. So first, At each single frame, we just get a binary mask telling you what is foreground and what is the background. And then through all of these cubes, we just get the ratio of the foreground pixels with respect to all the pixels that are in the cube. And then at training time, we just learn a threshold that will tell us at some point, and that's one cool thing from the system, is you can actually say how many true positives you're going to sacrifice. And you have to make some commitment there. That's as well as the system that can go. Then for the label assignment, the data doesn't come in cubes, right? So we have to convert those annotations into our cube format, and we just do it by dense sampling as we were getting all the proposals. And we estimate the spatial IOU between the proposal and the ground truth cubes. And then just follow the faster RCNN strategy to select the positive and negative samples. And finally, for the proposal evaluation, we just take an oracle approach where we assume a perfect classifier by using the assigned labels, and then we just pass through the following steps such that we can, of the activities and the metrics which we want to actually focus on. And then we just estimate the upper bound of our proposal estimator. Then for the activity recognition, we just used a multi-label classifier, basic stuff, binary cross entropy loss. We just weighted by the proposal scores. Then we balance the positive and negative samples per activity. We also balance the samples of different activities. And for some activities, which we could actually get some data from outside the current data, we just balance those as well. And then we do an action-wise late fusion where we have different models for each action. Then, as I mentioned before, you could have tons of duplicates, and we want to get rid of those. So the way that we do it is we just take one timestamp, get the mean score of these overlapping activities, and then once we've got the mean, we inject them back into these cubes, right? And then we just select the cubes that have the max score, and you just add them up like during all the scores. And then we, through a grid search on the validation data set, we just learn some thresholds to detect what's the best proposal that we want to take. And then for adjacent instances, we merge these into one instance, temporally speaking, because you can have all of these adjacent through time. So would you just merge them together, and then you get rid of those duplicates, and you do the same spatially. So we are managing both the temporal and the spatial aspect of the deduplication. And then we just apply an activity type filter. For instance, this is just heuristics where a car could not sit down, right? That would be, yes. Oh, sorry. And just the experimental results, implementation details, everything is quite simple in here. The evaluation protocols as well just told us what we did, and these were the results. Just a tiny note here is, yes, we got the best results on AOD, and we were lower on AD, but the AD is not considering the spatial aspect as we are in that case, and also we were hyperparameter fine-tuning towards the AOD task. And as conclusion on future work, I just presented to you Argus++, robust real-time activity detection. The main core of this is the overlapping spatiotemporal cube proposals. We showed superior performance in CVPR, ActEVnet, and many other challenges on the past. And in the future, what we would like to do is test this framework on more scenarios using drone videos. We want to refine the deduplication and add joint training objectives. And it would be really interesting to see if it works on zero-shot and few-shot activity recognition. Thank you.
Okay. My name is Zacchaeus Sheffer, and I will be presenting UCF's activity detection system for the ActEV Net Challenge. The videos here aren't playing, but I think most people are familiar enough with the data set that it won't be too much of a problem. There are several factors that compound to make this challenge particularly difficult. To be as realistic as possible, the videos used are untrimmed and may or may not contain activities. They include a wide variety of activities involving humans and vehicles in indoor and outdoor settings. Each activity can be single actor, include interactions between actors, and interactions between actors and objects. Because videos are untrimmed, we must find when and where actions start and end. Here we have our system overview. First, we split activities into clips and perform object detection on those clips to obtain tracklets. Those tracklets are assigned to objects, or assigned to object IDs using the IOU-based sort tracker. And each tracklet is then classified, possibly generating multiple class predictions per tracklet. And the tracklets are merged using object IDs into activity tubes. Finally, the predictions are passed through a post-processing block to smooth out and remove duplicate predictions. There are 3 steps in localization. First, we detect objects with a YOLO v5 model to find where objects are. Then we remove stationary objects using a MOG background subtractor. Finally, we assign object IDs using the sort tracker so the same object gets the same ID over time. Here we have an example of object detection, producing many predictions. This is too many predictions, and most of the objects are stationary. For this reason, we use the MOG background subtractor to remove extra predictions. It's simple to implement and reduces false alarms by 40%, as well as speeds up our system by 200%. So these videos aren't playing, but basically the idea is that most of those bounding boxes that you saw in the previous get removed in this process. For the object tracker, we use the sort tracker. So in this case, consider existing detections 0, 1, and 2 from previous frames, and suppose we have a new detection A. It has no overlap and is thus considered a new object. Here we have new detection B, which overlaps with 0, so it is assigned object ID of 0. Finally, detection C overlaps with 1 and is so assigned object ID 1. Here we have the improvement in performance after switching from pixel-wise localization to our object detection method. Ideally, it should have higher activity recall, and we were able to get 22% higher recall at a 0.9 ground truth overlap threshold using this new object detector system. For activity detection, we treat it as a multi-label problem. We use tubes extracted using the ground truth to train a 3D CNN backbone with sigmoid activations and a standard BCE loss, where each class is treated independently. While training on ground truth extractions is important, this causes problems as there is a domain shift when trying to evaluate on tracklets generated by our object detecting system. To account for this, we extract tracklets using our localization method and assign a label based on the ground truth. Then those tracklets with the generated label are used to train our system during, to train our model during training. Another problem encountered in this challenge is the class imbalance in the data set. As shown here, most notably, the most common class talking occurs more than 1,000 times as often as abandoning a package. We account for this using partial label masking. To learn multi-label action correlations, we use the log sum exponential pairwise, or LSEP loss, which is based on a BCE loss. We pair this with the aforementioned partial label masking to get our best results. Another trick we use to improve performance is to use knowledge distillation to compress the model. Here we have a standard knowledge distillation setup where the student learns from the teacher using ground truth labels as well as soft labels from the teacher. Without the teacher, the SLIM model performs 8% worse. Additionally, we employ a second stage knowledge distillation using an ensemble of 5 compressed models used in the knowledge distillation in the slide before. This seems to allow the model to learn better multi-label action dependencies, giving another 4.2% boost in score. Here we have a diagram of this stage of distillation. Remember that we've already distilled all of the teacher models in the way before, and we're using the same architecture for the student model. So we're able to add an intermediate activation layer loss that is just another loss term, in addition to the soft label loss and the loss with the ground truth. For post-processing, we have two steps: tubelet merge action split, which extends detections along a track and converts multi-label detections into several binary labels, and non-maximum suppression, which removes duplicate detections. For TMAS, first we chain tracklets together using the object ID from the object tracker, and we create a prediction for each class output above a certain threshold. This means that one track can contain multiple actions. We achieved our best performance when we maintained the aspect ratio of tracklets that were extracted and sent to the classifier. To maintain the aspect ratio, we extend the shorter dimension to square the bounding box. This contributed to overcounting of detections, as increasing one of the dimensions often caused it to overlap with nearby actions. So we needed a way to undo these duplicates. Here we have an example where one bounding box encompasses possibly many other actions. Here we have the SRL leaderboard. We placed second in the majority of metrics, but not the one that was chosen. I think this, so, or this might be out of date. Also of note is that our system placed first in the SDL unknown facility leaderboard. This is noteworthy because this is a real-time challenge as well, and it's also on the MAVA dataset. And we don't have access to the test data, which uses entirely unseen cameras that are not available to the contestants. Finally, we have our results from the TrekVid 2021 challenge. This one used the VRET dataset and evaluated on known cameras. We placed second in this challenge. The unknown facility challenge is important because it shows how well a system generalizes. This plot gives the drop in performance from switching to unknown facility evaluation from known facility evaluation. A perfectly generalized system should have no drops, so lower values are better. Our system achieved the best generalization among the teams. This plot shows the probability of misdetection versus the relative processing time. Our team performed the best while still being faster than average. That's ours at the bottom here. In conclusion, our system is real-time and generalizes very well to unseen data. We built upon our legacy system by replacing localization with tracklet generation, improving the training of our classifier, and improving the post-processing system. We were the top system for the SDL unknown facility leaderboard, and runner-up for the TrekVid, and runner-up for the ActEV SRL evaluation. Thank you.
Sorry, I have a question here. This is Li Junyu from the CMU team. I want to inform the audience that if you currently check the ActEV SDL leaderboard,
you want to finish that? Yeah, if you could lift the laptop. No, I think the presentation is on. Do you need to stop it or?
Yeah.
Okay. And video as well.
All right.
Video. Did you click it?
That's it. Can you see it?
Cool. All right. Can you all hear me? Cool. All right. Hi, everyone. We are the SoccerNet team, and today is the great reveal of our results for the SoccerNet Challenge 2022. This year's challenge was a team effort with many players from both industrial and academic backgrounds. And on behalf of all of them, Anthony and myself will present the results of this year's challenge. First, a few statistics on the SoccerNet community that we've built over the last 3 years. We had 25,000 visiting our website from 163 different countries, so definitely a worldwide impact and community. The most active countries are US, Japan, China, with a good participation from European countries as well, divided into statistics because there are many European countries. We're good. We built a community on Discord of 300 members that are following our activities with SoccerNet. And this year we had more than 600 total submissions for all the challenges. And we have gathered an impressive amount of views on our YouTube channels as well. So feel free to join us for more exclusive contents, including this, including tutorials and most probably the recording of this presentation. Now, SoccerNet is all about video understanding for soccer. But why are we interested in this field? Well, it has several applications ranging from action localization, automatic video summarization, video retrieval, automatic generation of statistics, and so on and so forth. So SoccerNet is an attempt of providing data, the benchmarks, the challenges that could benefit for the soccer research community. It started in 2018 with the release of the videos for 500 games, soccer games from the main European leagues. It was then successfully extended with more temporal understanding from a broadcast point of view, and which includes different tasks such as action spotting, camera shot understanding, and replay grounding. And then a few months ago, we also extended the annotation with spatial information on top of the previous temporal one, such as the localization of the field and the position of the players from multiple point of views. So it enables tasks such as field localization, camera calibrations, and player re-identifications. And this very CVPR, we have published also a workshop paper on multiple player tracking in SoccerNet videos, in soccer videos, which gathers additional spatio-temporal type of annotations. So over the last 4 years, we have gathered more than 5 million types of annotations, which is huge and makes SoccerNet one of the largest data sets for sports video understanding. And it solves for a wide variety of tasks related to, again, soccer video understanding. But for more complete presentation of the SoccerNet and its evolution in time, I invite you all to our keynote presentation during the CV Sports workshop tomorrow at 4:15 p.m. But to summarize, in this year's challenge, we introduced 6 different tasks, which are action spotting and replay grounding, like last year, player tracking, pitch localization, camera calibration, and player re-identifications. We split them in 4 main challenges, with each of them a money price of $1,000 offered by our generous sponsors. Today, we will reveal the results for action spotting and replay grounding, as well as player re-identification and player tracking. The result for the pitch localization and camera calibration will be released tomorrow at the CV Sports workshop at 5 p.m. in a dedicated session for this. All right, and I'll leave the floor to Anthony for the next part.
All right. Hi, everyone. So yeah, I'm going to talk about the results of the action spotting and replay grounding challenge. So action spotting is the task of localizing when and which soccer action occurs in long untrimmed videos. So we gathered 550 broadcast games. 500 of them are annotated for training purposes, while the annotation for the remaining 51s are kept secret to preserve the generalization and are used for the challenge set. So the task consists in localizing 17 different classes of events occurring in soccer games that are the most common ones, and they are annotated with single timestamps. So similarly, replay grounding, which is our second task, is the task of localizing when an action shown in a replay occurs in the complete broadcast game. So we leverage the same 550 broadcast game as for action spotting, with now the scope of localizing the exact timestamp the action shown in the replay occurs in the live broadcast feed. So you can see that task as an action spotting task conditioned by a replay clip. This is why they are grouped together. So these two challenges are sponsored by Synergy Sport, a division of Sport Radar, with a $500 prize for the winner of each task. And I will leave you with a presentation of the company now. Yeah.
Magic happens when the play is made, the dart's thrown, the serve's hit, and the ball is kicked. Everything will change for millions of people around the world. It's in that moment, as our hopes soar, that we're all connected by a love of the game, by the passion we share, and by the need to know what happens next. It's here, where sports and entertainment intersect, that Sport Radar operates. We deliver essential sports data and audio-visual content so that the sports experience is even more intense and interactive. Sports fans can anticipate and analyze based on our predictions and statistics. Clubs and federations can reach new audiences through innovative commercialization platforms and the compelling presentation of their sport. Sponsors can connect with fans at the critical moments before, during, and after the game. And bookmakers can receive services ranging from statistics and odds to fully managed outsourcing solutions. Solutions delivered by over 1,500 Sport Radar employees in offices around the world, as well as a global network of highly trained data journalists who are closely monitored for quality. To grow our business dynamically along with an ever-expanding sports market. It's just part of our visionary business model that connects and provides services to media companies, sports betting operators, federations, and sponsors. It's where our sports data and audio-visual products seamlessly link with our financial betting service offerings and media services. With both our world-lead integrity services that help to detect and prevent match fixing and preserve the integrity of sports, and our rights holder solutions that provide cutting-edge technologies and services to unlock the full potential of data. It's this unique blend of raw data, marketing solutions, and digital sports advertising that turns innovation into value, enhances global brands, and connects us deeply with our partners. So, when the next kick changes lives, Sport Radar makes it happen.
All right. So without further ado, let's dig into the leaderboard now. So here are the teams that participate to our challenge this year. So as you can see, we had 12 different competitors. And in third position, we had Weili and its team from Oppo Research Institute, Zhejiang University, and East China University of Science and Technology. So congratulations to them. And there's going to be a lot of teams, a lot of applause. That's cool. So in the second place, we have the PTS team with James Hong and its team from Stanford University and Adobe. All right. And in the first place now, so some drum roll, and we have Joao Soares and its team from Yahoo Research. So a big congratulations to them now. So we will now have a short talk of Joao explaining his method for action spotting.
Hi, I'm João, and I'll briefly describe our submission to the Action Spotting Challenge, which was based on a recent approach that uses a dense set of detection anchors. This is joint work with Avijit Shah, and we're both with Yahoo Research. Our method is unique in that it uses a very dense set of output detection anchors. We define an anchor as a pair formed by a timestamp and an action class, and we sample these timestamps densely at a rate of 1 or 2 per second. For each anchor, we produce two outputs. The first output is a confidence score, which should be 1 within a small time window of an action and 0 otherwise. The second output is a small temporal displacement, which should indicate for each anchor exactly when its corresponding action occurred. The figure on the right illustrates a set of desired output values for a single action class. After running the model, we post-process its outputs by displacing each confidence score by its corresponding temporal displacement. We then apply non-maximum suppression to obtain the final result. Our experiments showed that adding the temporal displacements provided a large improvement in the tight average MAP metric without affecting the original average MAP metric. More details on the approach can be found in a preprint that we put up on arXiv just some weeks ago. Now I'll quickly go over some improvements that we made while working on the challenge. These are not described in the preprint, but we're going to publish a separate technical report containing all the details and related ablations. For the challenge, we trained our model on all the available label data from SoccerNet. We also resampled the pre-computed features that were provided by Zhu and colleagues from Baidu, from the original 1 feature vector per second to 2 feature vectors per second. We then used a standard late fusion approach to combine a model trained on these resampled features with one trained on ResNet features. Finally, we used a soft version of the non-maximum suppression algorithm and made sure to tweak its window size as to increase tight average MAP. Thank you all for your attention, and a special thanks to the challenge organizers for hosting all these really great challenges. Thank you.
All right. Thanks. Big thanks to Joao for his great presentation of his work and for his amazing work on our challenge. So this year was a very fierce competition for action spotting, as you can see on this slide, with the metric on the y-axis and the time on the x-axis. And you can see that there was a lot of different teams competing in some clusters. So for the insights of what worked well for the teams arriving at the top, we gathered a bit summary of that. And so basically, from last year, where most people used CNN to extract features and so on, now we have the transformers network that have really taken their place for the different winners here. Also, a shift between context aggregation to self-attention mechanisms, and a big mix of spatiotemporal features, but also we had some teams who used the audio features as an extra input to further improve their performance. Now on the spotting end, it's mostly adapted from the TAL methods, so temporal activity localization methods, and grouping actions together and so on. We also had some team that did some end-to-end training, which is very impressive because the amount of data is so large, and with videos, it's very complicated to do so. So we had also this kind of stuff. Now we can move on to the replay grounding leaderboard. And as you will see, it's a bit more sparse because we had only one team competing on it compared to our baseline. But the winner is so it's also Wei Li and its team from Oppo Research Institute, Zhejiang University, and East China University of Science and Technology. So congratulations to them. And here is a video of them explaining their replay grounding method.
Hello, everyone. We are the team from Oppo Research Institute. We are glad to share the ideas with you here, and we'll introduce our method below. I'm Shi Mingcheng. The introducers are Jiaming Chu, Wei Li, and me.
Replay grounding consists in retrieving the time step of the action shown in a given replay shot within the whole game. We found that the clip after the time step of action contains a lot of discriminate information. In order to make full use of video information, we transformed the program into a temporal action detection task. Specifically, we extract 120 seconds video features before the replay time step as input. We set the label time step as the starting second of the segment labeled with 3 seconds length. In this way, Predicting the time step just is predicting the starting second or segment label.
First, we learn discriminative features as input of TAL to distinguish the information before and after labeled position. We design two atomic action clips from one labeled action time step. The 6-second features are clips from 2 seconds before the action time step to 4 seconds after that. In 3-second step 1, 2 labels are constructed with 1 timestamp. With these two kind of clips, we train 2 swing transformer classification models to learn different action characteristics.
With 2 features extracted by classification models, we getting the features or replay and pulling it to one channel as main replay feature. Then we concatenate the main replay features with each feature within sliding windows. To get more positive samples for training, we synthesize positive samples manually.
We apply a faster RCNN-like network in temporal action detection. First, we process the feature sequences with a base module to extract shared features. Then, we exert a proposal generation mechanism to obtain most credible course proposals. Proposals and shared features are further utilized to get more accurate boundaries by boundary regression refinement module. At the same time, shared features and proposals are employed to get the semantic labels of action instances with context adaptive proposal module. Now, we present our results in the table. That's all. Thanks for your listening.
Right, congratulations again to them. Are any of those 2 winners actually in the room? Not sure they could actually make it, but anyway, if you're around, let's catch up later on. So, all right, let's dig into our second challenge with the task of player re-identification. So player re-ID is a task of identifying each player across different camera views. We gather 340,000 thumbnails of players with specific classes based on the roles of those people between player, goalkeeper, referees, and staff. So the task consists in retrieving the same players from different camera views. So the challenge was also sponsored by Synergy Sports, division of Sports Radar, and with a $1,000 money prize for the winner. Here are the team who participated in the challenge. At least 13 of them improved upon the baseline. And in third, we have Siyu Chen and its team from Meituan. Congrats. In second, we have Wonshuo Wang and his team from Tencent U2 Lab and Shanghai Jiao Tong University. Congratulations to them. And finally, in first, we have, drum roll, Runze Zhang and his team from Inspur Electronic Information Industry. Congratulations to them. Here's videos from them explaining their methods.
Hello, everyone. It's our pleasure to share our solutions in the SoccerNet Player Re-Identification Challenge this year. I would like to give a video recorded presentation of our work. From left to right, our team members are Ringang Li, Yaqian Zhao, Hongwei Kan, Zhenhua Jiuo, Beoyu Fan, Runs Zhang and Xiaochuan Li, respectively. I will introduce our work from the following aspects. SoccerNet dataset is collected through the broadcast soccer games from the major European leagues. It has some difference to the normal person read. Person read is a representation task, which needs to distinguish different persons in different circumstances. But in the SoccerNet player read, the distinguishment is based on the action. So the player read can be considered as the action-wise person read. It means that the same player contained in different actions is regarded as different person IDs. The dataset contained 13,965 actions from 443 soccer games and 1.54 boxes per id on average. Therefore, there exists serious sample imbalance. We firstly removed the IDs whose images are less than 3. We experimented with different removed numbers and the results are as follows. Then we optimized our pipeline. We selected different modules according to the backbone, embedding head, loss function as well as ensemble tricks. For the backbone experiments, we selected efficient net, convnext, swin large and resnet st and finally selected the resnet st. For the embedding head module, we compared common linear, arc softmax, cos softmax as well as circle softmax. Finally, we combined the arc softmax and cos softmax and obtained 83.0 map in the test phase. As for the loss function, for the multiple IDs even removing the IDs whose images are less than 3, we employed the focal loss and boosted another 1.07 performance in the test phase. We experimented the data augmentation to strengthen the robustness. We selected the color jittering, auto, augmix, random patch, random erase as well as affine. The final combination is CJ, auto, ray. The probabilities are all equal to 0.5. Finally, we ensembled the tricks in the common person read such as we rank, multi-resolution input and model fusion, unsupervised domain adaptation for the challenge phase. The final result is 91.68 in the final challenge phase.
All right, thanks and congratulations again. So this year again was fierce competitions with several participants participating in this new challenge. As you can see, they were all battling for a few points here and there, and you have the complete listing on the left. So a few insights on what was interesting in this re-ID from the report that we received from all the participants is that most of them were using the fast re-ID framework. They also do some pre-processing out of that. So they were removing IDs with a few samples. Some of them were doing unsupervised domain adaptation, which was quite nice because we have a specific domain of soccer and not necessarily like general player, general person re-identification. So some of them were using this Trans re-ID SSL baseline with VAT backbones pre-trained on LU person. And most of them also using some tricks like data augmentations, like vertical, horizontal flipping, random erasing, and so on and so forth. That's basically it. All right.
All right. So last but not least, we have our third challenge for today, which is on multiple player tracking. So multiple player tracking is the task of recovering trajectories of multiple objects in time. So we gathered 130-second clips with specific bounding boxes detection for players, goalkeepers, referees, staff, and the ball, most important. The task consisted in retrieving the tracklet of those actors and other objects in time, given then their bounding boxes. In other words, a tracking task that focuses exclusively on associativity at this time. So the challenge was sponsored by Baidu Research with a $1,000 money prize for the winner. And here is a very, very short video of the sponsor. So let's now go to the leaderboard. So this year we had 12 teams competing on this task. And in the third position, we had the Tactica team with a very impressive high score of 93%. In the second position, we have the CBI Out team, which is Fan Yang from Fujitsu Research. All right. And in the first position, we have Adrien Maglot and his team from Université Paris-Saclay, CEA in France. So congratulations to them. And now you will hear them present their very cool method.
Hello, and welcome to this short presentation about our participation to the first SoccerNet Tracking Challenge. For this edition, the player bonding boxes were provided by the organizer. The first step of our method consists in associating the bonding boxes between the current and previous frames by bipartite matching with an Hungarian algorithm. We perform two successive associations. The first one with an intersection over union criteria. The second one for the unmatched bonding boxes with the center distance as criteria. Only small bonding boxes are candidate to extend the ball track. This first simple tracking framework leads to an association accuracy of 74.1% on the test dataset. But the previously described algorithm cannot recognize the player when he leaves and then re-enters the camera field of view. We therefore leverage the previously generated tracks to fine-tune a re-identification network with a triplet loss. This model learns the player fine identification details such as hairstyle, skin color, or jersey numbers. Triplet loss positive samples are selected from the same track, while negative samples are selected from other tracks that appear at the same timestamps, to be sure that they correspond to a different player. We compute the mean re-identification feature of each track and match the closest with a simple iterative algorithm. This leads to an association accuracy of 84.5%. However, some track associations may not be physically plausible. For example, if a player leaves on the left side of the frame, he cannot re-enter from the right side shortly after. We prevent player teleportation by checking the compatibility between the player disappearing and appearing positions. We obtain a final association accuracy of 86.1%, which leads to a HOTA of 92.4%. Thank you.
All right, thank you, Zidane. So the competition was very fierce and a bit delayed with respect to the other challenges, but definitely interesting, fresh perspectives to tackle that task. All right, so for the tracking insights, basically what's really improved this year is a strong re-identification module and forecasting player motion, as you've seen, and with a strong soccer-centric priors, such as modeling camera motion and understanding player positions on the field. And now we'll move on to the conclusion with Silvio.
Right, a few last words about the conclusion in that SoccerNet and its impact. So we had a lot of impact in term like how SoccerNet growth. We never were expecting that much of a growth. We got a lot of interest in our website, YouTube views. We organized 6 challenges this year in comparison with only 2 last year. We had more than 600 submissions, which is great, and we gathered a large community of at least more than 300 researchers and passionates around SoccerNet on Discord. So we hope that SoccerNet will continue in the future to challenge the computer vision community in numerous tasks that will help the research community to progress in soccer video understanding. But that's not it. We also invite you tomorrow at the CV Sports workshop for our numerous talks related to soccer video understanding. We'll provide some information about the next steps for SoccerNet during those talks. And again, soccer, like soccer, is actually a team effort. So I want to thank all of our collaborators for their contribution, bringing SoccerNet to what it became over the last years. Thank you. And feel free to follow us on social media. Sure. So I'll maybe take that one. So highlight detection is it's somehow very subjective, like what's in highlight. So some people will focus more on the goal, some other on the foul, some of the substitution for some reason. So it's very subjective. We believe that we need a level of kind of understandability, like explainable AI somehow, And we cannot maybe expect that an AI will figure out what's the highlight you actually want to put. And with action spotting, for instance, we can have an overview of all the actions and create the highlights out of this. Now, it is something that is possible. There is like a little bit of research in highlight, like for instance, when do we cut a clip, for instance, for a specific highlight of a specific action or occurring. So this is the type of research that is kind of, we believe is interesting. And if you want to add something or, okay, cool. Thank you.
All right, so next we have Tran. So before I do the introduction, just give us like 2 minutes to do the setup here, and then I will do the introduction. Use the stage for Du.
So let's try to share a screen. Let me see if this one already here. Okay. So do we see this?
Great.
Okay.
Okay, can maybe give a quick intro.
Yeah.
All right, so welcome everybody. This is going to be the keynote session given by Tran, and I'm so excited to introduce Du because I think he's one of the pioneers in terms of like video understanding, leveraging CNNs. So I'm a big fan of like his C3D work, R2+1D work, and for sure he's gonna tell us more. What's his vision for long-term reasoning, from video representation to long-term reasoning. So let's welcome everybody to Tran.
Yeah, thanks Fabian for the nice introduction. So good afternoon, everyone. So how are people doing? Right. Yeah. So, yeah, so it's very excited to get back to in-person conference. So it's been 2 years I've been stuck in my room. Doing research, remote experiment with student thing. Okay, so yeah, I'm very honored and humbled to be here to share with all of you some of our latest work on video understanding and a little bit on open work reasoning. So without further ado, let's jump into that one. So here the outline of my talk today. So the first part of the talk, I would like to share with you some work on representation learning, mainly self-supervised learning with ROS models supervision. This is John work with like Bernard here and a couple more people. This was the thing that I excited to share because it's very, very simple, but when you put it in large scale data, it becomes very powerful. It's a little bit outdated, like 2 years back, right at the beginning of the pandemic. So, but still relevant a little bit. So also why, and after that, I will talk a little bit more on how we do open work, long-term video reasoning. So it's more like a little bit new topic that our team just recently picked up, and there are two main parts. One is what the task and what the approaches. So just overview, and then I try to make the talk is more informal. So feel free to interrupt and ask questions. I will pause at the end of each part and then get question, hopefully. Okay, and then yeah, I try to be good. So the first work is we published like 2 years ago at New Rips, concept of learning with Roche model audio video clustering. So this is joint work with Humam, Bruno, Alonso, and Bernard here. So the motivation here is we all know that for representation learning, if we have large scale data, we have annotation that well annotated and with the relevant taxonomy, we can train a CNN out. Now we can train the transformers on the top of that and predict supervised label taxonomy. And the good, and then it normally it gives you a very good video encoder. So you can use that one for classification, detection, localization, and so on. So the good thing about that is it works well when you have enough data, and also when you retrain, and you fine tune on downstream, that is well aligned. But the downside is it's not scalable. Let's say we cannot scale the annotation network to a few million video or more. And then also there's also problematic when you pre-train on some taxonomy that very, very different from your downstream task, and it not work out of the box. So what we can do is, and also another problem is that in the past few years, we always say fully supervised retrain work reasonably well. So when it comes to embedding, come to like encoder, so we just stick with like fully supervised encoder. So is there any possible for us to scale like for self-supervised, but you do a lot more data, but our form fully supervised with the medium or small scale data? So that's a question we want to motivate. So there's one related work on the image domain called deep clustering, in which they try to learn image encoder from a set of images without any label. So basically this idea is simple. So they start with random image like connect features using a extract feature. So you take the function f here, you extract some random features, and on the top of that, you do some sort of clustering, for example, k-mean. And after that, you use this assignment. So clustering assignment as pseudo label, and then you can use this one, go back and train your CNN. So basically you use pseudo label. Instead of like fully supervised, you predict a network like CNN to predict cat, dog. Now you predict assignment cluster 1, 2, and 10, and so on. And then up to a finite number of iterations, your CNN improve. And then when you improve, you go back and get your encoder and extract a new set of features, and you do it iteratively. And it turned out to be work quite well for image problem. You can learn a very good image representation. So that's cool. So what about video? Like it's very tempting to say, we can apply the same for idea for video. It's quite simple, right? But before that, let me give you another motivation. So let's listen to this audio. Can we predict what actually inside? Right? So probably a dog somewhere in the video. Similarly for this audio as well. Okay. So obviously you can predict like probably there may be somewhere in the audio or on the video. And in vice versa, if you watch this one with the audio, you can kind of imagine in your head like what kind of audio you would expect to hear in this video, right? So, and the same thing here, you can. So their observation is that there are strong correlation between audio and visual. How do we use this correlation to bootstrap the self-supervised representation learning? That's the main idea. So let's jump into it. So first, if we apply the idea of deep clustering into video only, so we can learn a video representation by this way, by the just naively extend deep clustering. Or you can apply the same idea to audio stream. You can learn the audio representation, but that is not something interesting because it's just a naive extension of single modality. We call it a single modality deep clustering. But instead, what we propose is here from video, we use the pseudo clustering of the visual stream to supervise the audio stream here, and vice versa. We use the pseudo clustering of the audio to supervise the visual stream. But the most important thing here is the audio and the visual need to be very well aligned so that you can get the correlation right. And then at the end of this process, you can learn 2 encoders, one for visual and one for audio, and also you can do a lot clustering as well. So this simultaneously do. So let's take a look at how we evaluate that one. So because we learn both audio and visual encoder, so we can evaluate on action recognition, where we evaluate on XMDB and UCF, audio, which is ESC, just white standard. And then here's the performance. So first, if we look at the blue bar, which is the baseline random dash, obviously it performs worse because the data set is kind of small. So now if you look at the orange bar, which is the single modality, like maybe extension of single modality, right? And then now the green bar is just the ROS model. So say like significant improve like 12% to 8% across the benchmark, whether it is visual or audio. So, but one may wonder, because you have two models and you do ROS model, there may be some cheat in here. You have in remodel capacity, right? And also you have some complicated optimization. Why do we just do like, here we do another baseline we call same modality ActEV, where we supervise two models, two audio or two visual, make sure that we have the same capacity and also the same optimization mechanism. But actually, surprisingly, that it's the same as single modality clustering. So that actually the correlation have here, not the optimization of the model capacity enrich. So that is just sanity check. So it's good. And then we further enrich the data side. Now that is the most interesting part of this. Okay. So because if you do it like only connected, it's not that interesting. But now we enrich the size of the data to see how self-supervised learning behave with when you have a lot more data. So let's say you start from like 250,000 videos, you enrich to 2 million on the way to 65 million. Okay. But on the right side, it's self-supervised. You see all of the tasks. You see the red or the orange bar, which is the orange and the blue is visual task, and the red bar is the audio task. But all of the tasks increase when you have more and more data, which is a good thing. There's no dependent on the pre-trained data. But on the other side, if you look at here, so if you pre-train on connected, it's always perform the best on the visual task, regardless it's the smallest one, right? And then if you see the one that perform well on the audio task, which is audio set, so that means there are strong dependent of the pixel or the audio that you use during retraining with respect to the downstream application, which is not good because let's say if you want to switch to another task, then you need to switch to another set of encoder, which is not good. In representation learning, you want to have like, oh, I have one universal visual encoder for image, another visual like universal encoder for video and audio, so on, right? So that is something that behavior that we don't want to see in representation learning. And then also in like self-supervised learning literature, people talk about like you take ImageNet, you root away the label and you say that self-supervised learning. But however, that means you still have been biased by the set of image you created. So that means still created, even you don't use label. The same thing for video, even you use connected, right? Here we want to understand whether it works for uncurated. That means here you see the blue one is we sample video from IG connected. Even we don't use label, but it varied by the set of like keyword by connected label. And the other one is just random. You just random go to Interam and collect a lot of data. So you see here we enrich the size from 1 million, 16 million, 65 million. You see like uncurated also improves, and then it catch up with the curated because of like there's also bias in sampling, right? But this is UCF 101. Interestingly, the same behavior also on UCF 101. The gap getting smaller when you have more data. But more interestingly is when you look at the downstream audio, actually at some scale, the uncurated already outperform the curated, which means in this case, IG connected has some bias in sampling, but that bias doesn't help them because the downstream data is quite different. So that means that's still like a powerful enough large data. It's just like how we get it to use in the meaningful way. And then finally, we compare ActEV with other self-supervised learning method. It's just like a little bit outdated. Okay, so back then, like we outperform most of the reverse self-supervised learning method, but more importantly, we use the same backbone, and then we use ImageNet retrain. In ImageNet retrain, we emblade the image to make it a video and retrain on the same backbone. But that is fully supervised, and then also connected, fully supervised. You can see here we do self-supervised, obviously with a lot more data. So there are 65 million videos, but we outperform fully supervised retrain on ImageNet or Keynote fully supervised with the same backbone. Okay, so you see here, even like the correlated or uncorrelated, both of them outperform the fully supervised, which is interesting because that is a question that we want to ask ourselves, whether we have a lot more data, can we compensate for the label that we spent like 2 years of annotation of Keynote? So that kind of like partly answer, but it's still like the downstream is still on the more side, small data set. So then on the other hand, remember that we also learn an audio encoder. So we test on audio, like on ESC, we perform the second best, and on this case, we perform actually the best. So, and beside that, we also try to see if the representation learning useful for action localization. And here, we take like the state of the art GTAG method, and then we just replay the feature. So we replay the fully supervised Keynote feature, the same backbone, with IG random or IG Keynote. In both cases, the features perform better because here in the localization task, Keynote don't have a lot of advantage here. So we perform that one. So it's promising. And here is some like visualization of the cluster. Remember that besides learning the encoder, we also do clustering as well. So here's some cluster. So this is, sorry. So this is a cluster, or this is audio cluster. Do clustering on Keynote. So that means Keynote, but we don't have the taxonomy here. We just cluster on the audio. So you can see this cluster seems to be like So this is more like aligned with Keynote because it's a playing back by, it's a Scotland instrument. But on the other hand, like the audio cluster on rank 10 seem to be not aligned at all. So it's more like engine sound. Yeah, you get some idea. So this one totally like unsupervised clustering, but it's not necessarily aligned with the Keynote taxonomy, but it's a meaningful cluster. And similarly, so for the visual, it's completely like the left one is just guitar, but there we did cover some kind of other cluster. Like this one is completely misaligned with Keynote taxonomy. It's just like text on the dark background, but it's just like automatically covered by FTC. And here is some technical message from FTC. So the first one is we confirm that broad model between audio and visual correlation strongly help self-supervised learning. And especially when you have a lot of data, you can get that signal, semantic signal out of that easily. And then the method that you we just presented is very simple. Actually, we try to be very simple so that we can scale to a large scale, scalable, and taxonomy and downstream are independent. So basically, you already see that when we read the side of the data, the downstream across visual and audio task performance increasing. So that's good thing. And lastly, RDC outperform Keynote and ImageNet fully supervised retrain with the same backbone. So that is just a proof of concept that whether we can read that part, it's not a big deal, but actually it's an interesting experiment to share. So let me pause here for 1 minute or a few minutes to take a few questions before I move to the next one. Yeah.
So thanks for your talk. So I was just wondering, what is one of the first works that started like playing with this interaction between modalities, at least in the supervised setting. But nowadays we are seeing a lot of cross attention, right? Like now everything is a token, and you can do very like simple stuff as well there. So I was just wondering if you wanted, like if this work has, you have to do the same work today with self-supervised retraining for multiple modalities, but you have access to these cross-attention transformers or whatever. What will be the approach, or like it's more like a maybe like what is the future of this? If you have
I see. Thank you very much for the question. I think there's a follow-up work from Oxford and also Meta doing some kind of Roche model in the, I'm not sure that they do transformer yet, but contrastive on the Roche model. But in general, when the backbone improves, those things can improve. So that two things should be separate. The backbone, whatever you want to learn. So basically, you have a backbone architecture. You want to learn that parameter, right? And on the other hand, you need to inject some kind of supervision. So there are multiple ways you can inject supervision. Let's say MAA or what kind of thing like mask out. So basically, you get the semantic within the context of the instance. Let's say you mark out something and you predict something that you get out, like you learn from the context of that. So this one is gross instance or the same instance but gross model. And then some other thing they also do like gross instance as well. Let's really more like gross instance because now you iterate between look at a gross example by clustering them, and then when you clustering them, you hopefully can have some kind of similar instance, and then now you train a discriminator to predict something correlate between them. But here a combination both of them because deep clustering is just gross instance, right? And then ActEV is gross instance because they use deep clustering, but they also gross model as well. And then the other one is just like which in the instance. So there are multiple ways you can, but it may be complementary. So yeah. Okay.
Yeah, first of all, I think like just one comment. It's like relative and like the output from two supervisors, right? Like this is the trend relative. We're very humble to say that this is not something big, but I think was by being able to outperform two supervisors training is a great achievement. But I have a question about like the data itself, right? Like I'm just thinking like about the ID data, right? When I think about it, it's like social media videos, right? Where mainly the case like the video is edited and the audio does not align really well with the video, right? Like,
yeah.
I'm just wondering how the model was able to catch up this correlation, given that potentially a big portion of this data set may not be aligned. Right? Like, can imagine that many videos contain music or any other type of sound. So I wonder if you did any filtering or like do you have any vision or like any insights on how the model is?
Yeah, thank you for a very good question. And actually, if there are not much correlation between audio and visual, then basically it won't work, okay? Because we rely on that a lot, okay? But actually, when we try on a random video on Instagram, I think some of them, they have like no correlation actually. Let's say they have like music in the background instead of something that you capture. But let's say if the percentage of that is not too much, it won't hurt, let's say. But if like 50% of them is just irrelevant, then maybe you can have problem. Yeah. But even in the bias, you can get some kind of correlation in the bias as well. Let's say the music in the background has similar music, and then probably there's some reason for that to be similar as well, but that's not strong as the natural sound of the object observed in the video. But that's totally legit concern. So your question is that whether we can use the audio encoder here and then some sort of like correlation and then do recommendation, right?
Yeah.
So it may work, but someone need to do a experiment before confirm. So I don't want to claim something that without experiment. Yeah. Okay. Great. Thank you, everyone. Let's move to the next part. So the next part is more like on how to do open work segmentation. And let me give you a little bit motivation why we are interested in that and why it, like the title of the talk is video understanding, but why do we just do open work segmentation? That's weird, right? So now let me explain why we're like that. Okay. Hopefully you will be with me in the next 15 minutes. So few years ago, when we think, can we make video understanding in the wild, which means take a random video, apply whatever video understanding now today, and it any problem. If not, then we're done. We don't understand this song. I just have nothing to do. I find something else to do. But actually, there's many problems. Let me tell you some of the problems that we observe at Meta. Even like the state of the art model trained on kinetic perform very high, like 80%, right? And then when I take a random video of me sitting on the meeting, put the phone on the desk, it predicts talking to the phone. I don't touch the phone. So see the problem, right? The problem is the current classification with the closed work taxonomy. Just try to make whatever visual cue to make it more reliable to predict that. But that's the one problem. Let's get a couple more problems. Let's say in the real scenario, when you want to have the embodied AI, robot, autonomous driving, many times you see novel objects you never see in your taxonomy. How you deal with that? It's completely insane. And then, but that is just one problem. The second problem is that now we are talking about 10-second video understanding, or less than 1 minute video understanding in Keynote. I'm talking about the most popular benchmark for video. But in reality, most of video is just like a few minutes. Or if I want to work like 30-minute video understanding, or 1 hour, or 1 day long, how do I do that? I have no hint. How can I do it? I stuck, right? And even more than that, let's say for now, we have awesome work on classification, action detection, localization. But what if I just ask a simple question? I have a video captured by my smart glass for a day or half day, and I ask, what activity I have done with this object this month? So can it answer me like, okay, you do like making hot food? What tool are you doing cooking? When did I make hot food with this microwave? So there's a lot of questions human can do, or even I can ask my child 10 years old can answer easily. But this one, it's just no hint. We optimize well for detection and recognition. What are we missing? We're missing a lot of this, right? It's just simple. Then we don't understand it very far away from being solved. So that's a good thing. That's good news. So, but the bad news is there are many problems to solve. Which problem we want to solve first? There are many problems, right? So ideally, I really want to tackle the long video understanding, but the long understanding is also difficult. But before moving to that, let me give you another motivation. So here, a random frame we take from Keynote, just random. And we take a master CNN, train on Coco, taxonomy 80 classes. We detect some of them, miss many of gym equipment in the background. That totally understand because it's not trained to detect all of the objects. Second, we go to the Google Cloud API, which claim to be trained on a taxonomy of 550 plus category. It still miss many objects. So what are going on? So then we add a human annotator to level, let's say, level all of the object in the video that you see. They level all of them easily. I mean, for the small object, we don't care much, but that's a lot, right? And further, when we look at the statistic, this is statistic done in Keynote video. So like a subset of Keynote video, so that there are 57% of objects in Keynote are non-Coco. So that means even state of the object detector means like more than half of the objects. What can we do? And then another question is that why human can easily identify unfamiliar object, even a UFO or some weird flower and then robot, right? So how we want to tick robot to recognize new object or something. That is a problem that we want to unlock in order to want to like do truly open work video understanding. But upon us, if we do this, then the game for video, long video understanding can be changed. Let's say for now, the majority of the model is pixel-based CNN. Basically, you train transformer, CNN, whatever thing on the loss center, detection, classification loss, backdrop on the way to the pixel. So that's why you cannot go longer, because NVIDIA GPU just not allow you to go beyond 32 gigabytes. So that cannot do that, right? So what if I turn the game instead of pixel-based CNN or pixel-based modeling, we can do like entity object-based modeling. You can do graph convolution, or you can put transformer on the super voxel. I can do like a few hours, over 1 day long video understanding, right? But that is something like more like bottom up or hybrid, bottom up a little bit and top down. But that maybe can figure out later. But the fundamental problem in key blocker is how we group the pixel in entity, regardless what kind of object taxonomy. We want to get all of the object in the video, not just 80 category. So that's the problem we introduce here. Open work is on segmentation. So let's take a look at this. Not sure the video playing. Oh yeah. So see, like we label assortedly all of the object we seen in the video. And then some fast-moving objects and very diverse content. You see like ego-centered or third-person views, and you see like different like either spark object or dance, and even like a lot of professional video as well. This is a subset of Keynote, so we have just like relay the annotation on the top, but just restate the problem statement. Open work segmentation is the problem of grouping the pixel in the image and video into the entity, regardless whether it belongs to the training set or not. It's just like as long as it are semantically coherent object, we want to group them together. So that if we can do that, the computation for the next step should be easy. So then the motivation is that if we can do this, it may be enable open work reasoning. And also it may be enable long video understanding. You can do like a lot longer transformer on the top of CNN or rack convolution, and possibly enable flexible tasks. So now your log not necessarily become detection and classification, but can be something else, because your taxonomy not depend on Google or whatever taxonomy. It's just entity. On the top of that, you can do anything, and don't let your imagination stop there, right? And here, so some statistics of that. So in terms of video, it's small, but we annotate it very high FPS. In terms of number of frames, it's like 100K, but taxonomy open work and very dense. So some take-home message from UVO is, we believe that open work instant segmentation is one of the foundation tasks which possibly can enable open work reasoning, long-term video modeling, and flexible tasks. So we currently working into the last two problems, but we will have some results coming out. But we are looking into how to use those kind of things to do long video modeling, also do flexible inference tasks beyond the detection and recognition. So, and then we already released UVO with and then we also have challenge at ICCV last year and at ECCV this year as well. That's pretty much. Before I jump into the next talk, I can take like a couple of questions. Yeah, I think I have time. 29 minutes. Yeah. Yeah, please.
So this reminds me a lot of like early vision like approaches to kind of group pixels together into super pixels, like I don't know, like multi-scale combination group.
Yeah.
So what is, I mean, I guess the problem is hard to define even for humans, like segment all the objects, but how fine do I go, right? Because I could start segmenting the shoes of the human, also the sock, also the jacket. How do I define, and that's why I can relate this hierarchy of the stuff with the early vision one. So how do you guys figure this out, or like, or what do you have there?
You got it. So I think you have a very good question. You asking about like the subjective of the hierarchy in terms of the object definition. Yeah, let's say whether my thoughts are an object, or my foot not be an object, or just my head is an object, or yeah, something like that, right? So I think if you evaluate on the matrix, should be fine. So basically, you kind of, if you have dense everything of them, and then you do AR, and then you have enriched like more number of proposals. Let's say if you can recover how many of them. Let's say if you have this one, or pretty much like if, I mean, it depends on, if you just look at AR only, then it'd be fine. But if you look at precision or something like, then you may be, because that is, but that's still the problem. I can see that's still the problem. But AI can mitigate the problem a little bit, because otherwise, let's say, but the thing is that if you have dense annotation, then the problem be less sure. Because if you look at some other one, let's say Coco, there's a lot of object in the background never been labeled, then you'll be penalized if the model predict that object as well. But if you have dense of them, then that problem be less problematic. Yeah. So, but yeah, so then I think the next part, we talk about how to approach that one. It's just one approach, and this one we're going to be published this year CVPR as so this was here we try to, so previously I present the problem and the benchmark. So now we look into the methodology. So how we do that? So the motivation here is that if you look at the route routes, here it's on ADA. ADA also has a lot of segmentation. If you take like a bottom-up approach like select t-shirt, which you have no learning at all. So basically you have a lot of over segmentation and small prediction, like over segmentation. The good thing about select t-shirt is there's no taxonomy, there's no bias in class, but there's a lot of noisy and over segmented. And on the other hand, if you take the math async and you train for our background only, then you also miss a lot of objects that not in the annotation of COCO. So that's not good thing. So that you can only detect 5 out of 20 and 4 out of 20 here. So then the observation is, oh, okay, just missed a lot. So, okay, so the bottom up like select t-shirt or something, it's good. It generates robot to unseen lab because there's no concept of learn concept seen and unseen. But many fair positive mostly produce over segment part. On the other hand, if you do top down and you adapt into 4-hour background classifier, like you train math async and you turn the recognition head into 4-hour background, the good thing is that it can predict the whole objects and less under segmentation, but it be been biased by the contextual cue of whatever class that you see. Let's say most of the top-down approach will be biased by the context. And then because the context bias, it cannot detect the new category. So what we say is that, what if we learn something a little bit low so that it's not biased by the context, but also can enjoy the generalization. So here we look into pixel level pairwise affinity. So let's say you define whether 2 pixels belong to the same object or not, but here we want to learn it. So here, let's say the definition here is that if all of this belong to, let's say, the same neighborhood, but this one is not the boundary. So basically, it's just a binary vector of a neighborhood, and then here is the prediction of the pairwise affinity trained on Gaussian math only, but it can generate well to the zebra. That's interesting because it just look at local queue, but it has some learnable component because you train on FCM, you learn that. So interesting. So the task is predict binary vector and got the object boundary, semantic object boundary, and it's different from the normal ACT detector because ACT detector doesn't care whether the actually semantic or not. You see a lot of try in the zebra. We don't need that. We need the boundary of the object, tell whether 2 pixels belong to the same object or not. And it generally well to unseen lab. You already see here like the math trained on Gaussian can generate well to the zebra. And yeah, it's different from Max. A few more samples. Here also we see the math async or the FCN trained on only Gaussian math, but generate well to many other class. And based on the output of the pixel affinity, we do some symbol grouping here, the UCM or MCG. We can leverage more math from the other class. You see like orchards, the cow and the temple, but we just train on the math from the Gaussian. So that means we bypass the context bias of the top-down approach by inject a little bit low-level supervision and then grouping. So take that idea, how to use this kind of math to improve the general grouping model. So what we do is that first, we take the non-assorted segmentation math, whatever mean just like the number of math on the flow taxonomy, and we train a pairwise predictor. And when we use pairwise predictor, we run on the training images and we use grouping. You can use UCM or you can use MCG group to generate more mass. So you see like you can have more mass and then you go back and use the mass together with the route truth math you train another, let's say math async to predict on generate grouping network, because now we have more and more pseudo route truth. Let's take a look at the result. So if you train on the math async, so if you train on VOC on COCO and you test on non-VOC, and then here train on COCO, test on Elvis, or Elvis test on COCO. So in other case, let's say the baseline and this is bottom up. Bottom up means you can do the pairwise affinity plus grouping. It's improve a little bit, but here the end-to-end, like GGN improve mostly 8% or a few percent across different settings. And even like we can do open work in the white, which means we train on Coco and test on EDA without any fine tuning. We don't do any tuning, just like take it is, and it outperform the baseline by 4.5%. And also like train on Coco and test on UVO without any fine tuning. So that makes sure that it works in the white. So that is more. And then the same figure that you see at the beginning, now you see like GGN can get 14 out of 20 from the route truth. Admittedly, that's cherry picking, obviously, but you already see the number. So I'm not just cherry picking, hopefully. And then some more quantitative results. So here, route truth had like 81 objects. So GGN get like 30, or similar here, you get like 9 out of 13 compared with MathICNet. So beside that one, we see that like Bellwire free, they can generate a lot of pseudo route truth. What if we relate the pseudo route truth retraining with ImageNet retraining? What does it mean? Let's say you take the MathICNet, you start with ImageNet retrain and you fine tune on Coco. What if we take the MathICNet but retrain on the pseudo route truth and then fine tune on the same task, right? So that means we relate ImageNet retrain. So let's say we don't need ImageNet retrain. What if that? And then on the left side is the close work. That means you train on Coco and you test on Coco. That is close work. The traditional object segmentation just replace ImageNet retrain by the completely pseudo retrain. So we're still like 1.4% below the self-supervised. But on the open work setting, if you train on LVIT, test on non-Coco, or train on Coco, test on UVO and EDA, we outperform the ImageNet supervision. So that means even you can fully retrain on pseudo and fine tune on the data set, the target data set, we do better. So that means there's some kind of generic mechanism of grouping. So let me take the summarization. So open work segmentation is important and yet challenging task. And then we somehow found out predict the pixel level can get some robust to unseen last. And finally, our GNN outperforms the baseline by good margins. And let me conclusion and I'll take like a couple of minutes to take a question. So far, we see that large scale representation learning has great potential, whether it's XC or any transformer, when you have a lot more data, if you inject some kind of relevant supervision, you can get some powerful and universal representation learning out of that. And then we already see that we don't have many somehow overload something like new, but we haven't paid attention enough. Maybe there's a lot of challenge and volatility as well. So intersegmentation, which could be fundamental and interesting that to solve, because if we can solve that, it maybe open up opportunity for open work visualization or very long-term video understanding and flexible prediction tasks. So with that, I really appreciate you guys spend 45 minutes to listen to my long talk. I'm happy to take questions. Are we good? Okay.
Yeah, so I think like really exciting is trying to go to these open world segmentation. I think like you mentioned, like one of the motivations of it is basically you cannot fit very long videos for you.
Yeah.
I mean, we need somehow have this kind of like no level understanding and path to high level data.
Yeah.
Yeah. But I wonder like if at some point like in time we have better GPU, we have better compute, let's say 10, 20 years from now, do you still see relevant like parsing the video like leveraging this kind of like instant segmentation? Let me explain. Like if we have better compute, we can actually feed the entire video. We still will still be able to actually feed this kind of new level representation to the long-term understanding model.
I see. Very good question. I think, yeah, so I think if you have unlimited GPU memory, let me make very hypothetical assumption. Let's say NVIDIA give us like unlimited GPU memory. So then if you do end-to-end, probably you can guess the most accurate with respect to your optimization loss on the top, right? Because that is just what you're looking for. But you forget about the efficiency as well. So efficiency also very important because human is not doing inference by look at everything, right? So, and then if you do long, even like if your model process every single pixel, it's not going to work. Let's say I give you like 1 hour or 1 day of video, and then it take me like to do just inference, like take like a few hours to do inference on that video. It's not possible, right? And then user just like ask you one query, latency like few seconds, answer me, and another query. So yeah, efficiency and also for storage as well. Let's say if you want to sell only relevant memory or something information, then a bottom-up approach is still relevant and it's still useful. And yeah.
Let me just follow up with my model, like as well, like in the long term, like do you see any role of reading, like as well, like the trend from the sun, long form video, like here, I mean, like now in the video, but do you think reasoning about reading?
Oh yeah, environment, right? Yeah, I think human also rely a lot on environment and using that trial to do attention selection or something affordance. And because you do conditional attention, basically, let's say if I miss something, I'm not looking everywhere, I just like looking somewhere that with the high likelihood of that happening, right? So yeah, that how human model much more efficient and low energy consumption. GPU is on the opposite. Yeah.
So you were talking about, so this is like an implemented step to go to long form.
Yes.
So once you extract these instances and these super pixels, then you can put many more on the GPU. But I was wondering, how do you actually put them? Like, how do you once you have this instance, how do you represent that instance to actually go on perform a task in a long form video understanding? What do you put, right?
Oh yeah, I see. Okay, so because I haven't I haven't worked on that exactly problem. We look into like internally we work on some of them. So then multiple way you can do. Let's say the basic way, even like very simple and engineering way, put everything and then got features. Okay, and then you can do heavily indexing source or something that is like something like Drake do it 30 years ago already. Right, nothing interesting. But what if you do on the top of that? Let's say you do graph convolution, or you tokenize them and put transformer on the top of that, or you can do some kind of memory thing. So let's say, yeah, and then I think there's a lot of problem how to organize the memory for efficient query tasks. Let's say in Ego 4D, we have similar task called episodic memory. But yeah, that is something that we are looking into how to do with long video understanding, basically. Hopefully that. Yeah. So that's many ways. So I mean, as long as we have something, even like we have the task for now, we even don't know what is the right task for long video understanding, right? Because let's say for long video understanding, recognition become less and less relevant, right? Because let's say 1 hour video, you predict single level, it's just impossible. And then in 1 day, it's even more impossible, right? So then if you have the right task, and then the rest is whether you want to do bottom up, explicit modeling or top down implicit modeling, it's just like the matter of you trade off between efficiency and accuracy. And then you have a lot of metric like how you like computation more like only per query, per inference, or how you create the model as well, like apply kind of built-in memory or create model or something. Yeah. Thank you.